So good morning. So in this video, I'm going to discuss about the applications of Ellingham diagram. So Ellingham diagram helps us to select suitable reducing agent as well as appropriate temperature range which is required for reduction of metal oxide into metal. But the two important application of Ellingham diagram, the first one is it helps us to select the reducing agent. Which one can be an effective reducing agent for reducing a particular metal oxide into metal? That is one thing. The another one, the appropriate temperature range which is required for reduction purpose. Temperature range for reduction. At which range of temperature the reduction can be easily carried out. So these are the two important things which can be get from Ellingham diagram. For example, if a metal oxide is more stable, then the oxygen will remain with the metal. Suppose if the oxide of an element used for reduction is more stable, then the oxygen from the metal oxide readily combines with the element which is used for the reduction, and in such a case that element can be an effective reducing agent for such metal oxide. For example, you have a metal oxide of formula MO. So with this you are using a reducing agent X. The oxide of X is more stable than this metal oxide, in the sense of now when this reducing agent X heated with metal oxide, then it will take up the oxygen from the metal oxide and forms a stable oxide of formula XO, whereas the metal can be separated. Okay, so this is the basic principle behind reduction of metal oxide into metal. Correct. So now let us see some important application of this Ellingham diagram with reference to some elements. Okay, right. So now look at this Ellingham diagram. You have formation of oxides of several metals, and in Ellingham diagram the temperature is plotted in x-axis and delta G naught value is plotted in y-axis. So according to Ellingham diagram, greater than negative delta G naught, more effective the reducing property. If a metal which has a higher delta G naught value, then that metal can act as an effective reducing agent for reducing other metal oxide into metal. Okay, right. Now here we are going to discuss the reduction between chromium oxide and aluminum. Okay, right. Now to reduce chromium oxide or chromic oxide, we can use aluminum as a reducing agent. When a mixture of chromic oxide and aluminum metal is heated, the oxygen from chromic oxide will be taken by aluminum so that it will become as aluminum oxide, whereas the chromium metal will be produced. So which means that aluminum can be used as a reducing agent for reducing chromium oxide into chromium metal. Correct. Now just I write the reverse of the same reaction. You have aluminum oxide Al2O3. With this, by adding chromium 2Cr by heating, suppose if this reaction occurs like this previous one, you are supposed to get chromium oxide Cr2O3 with formation of aluminum metal, isn't it? Whereas the first reaction is possible, the second reaction is not possible, because look at the Ellingham diagram. Whereas in the Ellingham diagram, chromium oxide is lying above the diagram, isn't it? This is a chromium oxide line. Then this is the aluminum oxide line. But generally according to Ellingham diagram concept, the metal which is lying below the diagram can act as a very good reducing agent for the metal oxide which is lying above. But when you compare aluminum oxide and chromium oxide, so aluminum oxide formation line is below the Ellingham diagram, which means it has greater delta G naught value. Aluminium oxide is more stable compared with chromium oxide. Therefore, the aluminium metal can be used as a reducing agent for reducing chromium oxide into chromium metal. Whereas the reverse is not possible. In the sense we cannot use chromium as a reducing agent for reducing aluminum oxide or alumina into aluminum metal. Okay, so that is how this Ellingham diagram is helpful for selecting the suitable reducing agent for reduction of a metal oxide into metal. Okay, right. So basically this is the concept which is lying below the Ellingham diagram can act as a reducing agent for the oxide which is lying above. Okay, right. And but here we are using aluminum as a reducing agent for reducing chromium oxide, isn't it? Is it possible to use aluminum as a reducing agent for oxides such as magnesium oxide and calcium oxide? So aluminium cannot be used. Aluminium cannot be used as a reducing agent. Reducing agent for reducing metal oxides such as calcium oxide and magnesium oxide. The reason is, look at the Ellingham diagram. Look at the Ellingham diagram. And see that in the Ellingham diagram, calcium oxide and magnesium oxides are lying below the diagram, isn't it? This is a calcium oxide line, this one. This is a magnesium oxide line, isn't it? Whereas aluminum oxide is lying above calcium oxide and magnesium oxide, isn't it? But therefore, aluminum cannot be used as a reducing agent for reducing calcium oxide and magnesium oxide, because the one which lies below is a effective reducing agent for the oxide which is lying above. Okay, there is the one important application, selection of reducing agent for reducing metal oxides. Okay, so that from this you can understand that aluminum is a very good reducing agent for chromium oxide, but because it is lying below chromium oxide, isn't it? But it is not a reducing agent for magnesium oxide and calcium oxide, because magnesium and calcium oxides are lying below aluminum oxide formation curve. Okay, right. Now there is a question based on Ellingham diagram. Okay, so under which condition aluminum can act as a reducing agent for magnesium oxide, as well as magnesium can act as a reducing agent for aluminum oxide. Okay, right. Now we are going to find out suitable temperature range. We are going to find out temperature range. We are going to find out temperature range for reduction. So you want to reduce aluminum oxide using magnesium as a reducing agent. As a result of that, you are supposed to get aluminum metal plus magnesium oxide, isn't it? Now, which temperature is suitable for this reaction? That is one question. Another one, you have magnesium oxide. Yeah, magnesium oxide with the help of aluminum. You are supposed to reduce magnesium oxide into magnesium metal 3 mg, and that aluminum will take up the oxygen so that it will form aluminum oxide. For the second reaction, what is the temperature condition? Okay, range of temperature which is required for this reduction. Okay, even this also can be predicted with the help of Ellingham diagram. Okay, so now look at the Ellingham diagram. These are the aluminum oxide line, then this is a magnesium oxide line. Okay, right. Now just see the point where these two lines are intersecting. Okay, you can see this is the point where the aluminum oxide line and magnesium oxide lines are intersecting each other, isn't it? Probably this may come around this, isn't it? So the temperature is approximately about 1600 or exactly 1623 Kelvin. So now this temperature is 1623 Kelvin. Okay, intersection point. Right now, so in this intersection point, left to the intersection point, magnesium oxide is lying below, isn't it? Right to the intersection point, aluminum oxide line is lying below the diagram, isn't it? Which means that below this temperature, that is below 1623 Kelvin, this can be used as an effective reducing agent for this metal oxide, which means below 1273 Kelvin, below 1623 Kelvin, magnesium oxide can act as a reducing agent for reducing aluminum oxide. Okay, right. So now, we want to predict the temperature, isn't it? So that magnesium acting as a reducing agent. So below 1623 Kelvin. Okay, right. Then look at the diagram again. Okay. Then above 1623 Kelvin, which line is lying below? Aluminum line is lying below, isn't it? So that above 1623 Kelvin, aluminum can act as a reducing agent. Aluminum can act as a reducing agent for reducing magnesium oxide. Okay, right. Now, the condition for second reaction, the temperature is supposed to be about greater than 1623 Kelvin. Okay, right. So from this, we are able to understand that below 1623 Kelvin, magnesium line is lying below the diagram, aluminum oxide is lying above. Okay, so less than 1623 Kelvin, magnesium oxide formation line lies below, aluminum oxide Al2O3 formation line lies above. But now, which is lying below can act as a reducing agent. That is, magnesium can act as a reducing agent for reducing alumina into aluminum below 1623 Kelvin. Okay, right. Now, above 1623 Kelvin, that is right to the intersection point. This is left to the intersection point. This is right to the intersection point. So greater than 1623 Kelvin, aluminum oxide. What is it? Aluminum oxide line lies below, and magnesium oxide line lies above the diagram. Okay, so as we discussed earlier, which is lying below is the reducing agent for the one which is above, isn't it? But therefore, above 1623 Kelvin, aluminum can act as a very good reducing agent for reducing magnesia. Okay, right. So now, we have predict the temperature range for these two different reactions, whereas first one, it is less than 1623 Kelvin. Okay, right. Then for second reaction, the temperature range is greater than 1623 Kelvin. Okay, right. So these are the two important applications of Ellingham diagram: finding out the suitable reducing agent which is required for reduction of metal oxide, as well as to find out the temperature range which is required for reduction of a metal oxide. Okay, right. We can see some more examples. Look at the Ellingham diagram, the iron oxide formation line and carbon monoxide formation line. Look at iron oxide and carbon monoxide formation lines. Okay. Actually, this is the carbon monoxide formation line. This is carbon monoxide formation line. Then this is iron oxide formation line. This one, isn't it? Right. Now, these two lines are intersecting in this point, isn't it? This is the intersection point. Right. Now, this point is at a range about 700 Kelvin, isn't it? So around 1000 Kelvin. This is around 1000 Kelvin. Okay, right. Now, so right to 1000 Kelvin, carbon monoxide line is below the diagram, isn't it? Above 1000 Kelvin, that is left to the intersection point, carbon monoxide is lying below. Carbon monoxide is lying below. Above, that is above 1000 Kelvin, that is right side, above 1000 Kelvin, iron oxide line is above the diagram and carbon monoxide line is below the diagram, isn't it? This is iron oxide line above the diagram, then carbon monoxide line is below the diagram, isn't it? Then left to the intersection point, which means below 1000 Kelvin, that is it, below 1000 Kelvin, iron oxide line is below the diagram and carbon monoxide is above the diagram, isn't it? So from this what we understand is, that is above 1000 Kelvin, above 1000 Kelvin, carbon monoxide is more stable than iron oxide, isn't it? So which means above 1000 Kelvin we can use carbon monoxide for reducing iron oxide, whereas left to the intersection point, what is it, left to the intersection point, which means that is below 1000 Kelvin, which line is lying below? So iron oxide line is lying below. In the sense iron oxide is more stable below 1000 Kelvin. So that from this you can give a suitable temperature range for reducing iron oxide by reducing agent carbon monoxide, so that above 1000 Kelvin only carbon monoxide is lying below, iron oxide is lying above. Therefore the suitable temperature range for reducing iron oxide into iron using carbon monoxide as a reducing agent is above 1000 Kelvin. Okay, so this was the reaction. Actually FeO is supposed to be reduced with the help of carbon monoxide into iron metal, isn't it? Now here the suitable temperature range is about greater than 1000 Kelvin, because above 1000 Kelvin, above 1000 Kelvin carbon monoxide lies below the diagram, lies below, then iron oxide lies above, and the one which is below as a effective reducing agent for the one which is lying above. Okay, I hope you understood. So that for reducing iron oxide with the help of carbon monoxide as a reducing agent, the range of temperature range which is required is about 1000, greater than 1000 Kelvin. Okay, right, done. So there is another question which is based on the Ellingham diagram. Which is the suitable condition, which is the suitable condition for carbon and carbon monoxide to act as a reducing agent, or otherwise carbon monoxide is more effective reducing agent than carbon below 983 Kelvin. That is less than 983 Kelvin, carbon monoxide is a effective reducing agent. Carbon monoxide is effective reducing agent. Whereas above 983 Kelvin, above 983 Kelvin, carbon is a effective reducing agent. Carbon is a effective reducing agent. So let us see this with the help of Ellingham diagram. Okay, right. This is example number 3, example number 2. Then aluminum oxide, magnesium oxide, that is example number 1. Okay, right. Now go for the Ellingham diagram. Right, now we have to look at carbon monoxide line as well as carbon line, isn't it? Okay, so this is nothing but carbon monoxide formation line. Then this is the line for carbon, isn't it? Okay, right. Now these two lines are intersecting over here. The temperature range is above almost around 983 Kelvin. So this is about 983 Kelvin. Okay, right. But now below 983 Kelvin, below 983 Kelvin, this is lying below the diagram, carbon line above the diagram, carbon monoxide line is below the diagram, carbon line is above the diagram. Then write to that above 983 Kelvin, this is carbon line. Actually this is carbon line, this is carbon monoxide line, whereas left side this is carbon monoxide line, this is carbon line, isn't it? Okay, right. Now you can easily understand from this. Okay, above the temperature 983 Kelvin, carbon line is below the diagram, which means above 983 Kelvin, carbon is a more effective reducing agent. Then look at on the left side of the intersection point, left to the intersection point, that is below 983 Kelvin, we have carbon monoxide which is lying below, isn't it? Which means carbon monoxide is a more effective reducing agent below this temperature. Okay, right. So now we come to the conclusion that below 983 Kelvin, below 983 Kelvin, carbon monoxide line lies below and the carbon line lies above. So that in this temperature range, carbon monoxide is a effective reducing agent. Less than 983 Kelvin, carbon monoxide is effective reducing agent because it has a higher delta G naught value, because it is lying below. So in the sense it may have greater delta G naught value and it acts as a effective reducing agent. Okay, then above 983 Kelvin, that is right to the intersection point, carbon line lies below, carbon monoxide line lies above. Okay, so that above this temperature, that is greater than 983 Kelvin, carbon is a effective reducing agent. Okay, right. So this is another question from which we can understand the suitable temperature range for carbon and carbon monoxide, which can act as a reducing agent for reducing metal oxides. Okay, so let me finish with one more example. Example number 4. So zinc oxide can be reduced with carbon into zinc metal, isn't it? Right now, whether carbon or carbon monoxide, which is a suitable reducing agent for zinc oxide. Okay, so effective reducing agent for zinc oxide. Okay, whether carbon or carbon monoxide. Okay, right. So again we go for the Ellingham diagram. So look at the Ellingham diagram. 1 minute. Right, where is the zinc oxide line? So this is the zinc oxide line. Yeah, this is the zinc oxide line, isn't it? Okay. Right. Now this is carbon monoxide line. Actually, this is carbon line, isn't it? Right now, look at this. So zinc oxide line and carbon lines are intersecting over here, isn't it? Right. Then this is the point where zinc oxide line and carbon monoxide lines are intersecting. Okay, right. Now when you compare carbon monoxide and carbon is having greater delta G naught value. Carbon is having greater delta G naught value compared with carbon monoxide, isn't it? So which means that comparing carbon monoxide and carbon can be the suitable reducing agent for reducing zinc oxide into zinc metal. Okay, here between carbon and carbon monoxide we can select the suitable reducing agent for reducing zinc oxide. So that for zinc oxide, carbon is a suitable reducing agent, so that it will readily reduce zinc oxide into zinc metal with formation of carbon monoxide. The reason is carbon monoxide has higher delta G naught value. It has higher negative delta G naught value than carbon. So the one which has greater delta G naught value will be the more effective reducing agent than anything else. Okay, so these are the different applications of Ellingham diagram. I hope you understood how the Ellingham diagram is helpful to us to find out the suitable reducing agent which is required for reduction of a metal oxide, as well as the exact temperature range at which a metal oxide can be reduced into metal. Thank you.